Hi, my name is Neil. This is a re-recording of a talk I did at the virtual Rust Edinburgh Meetup, which was online on the 25th of June 2020, about my first project in Rust, which I call Pirrigator, a portmanteau of Pi for Raspberry Pi and irrigator, and it's used for irrigating the tomatoes I grow in my greenhouse. Hence, growing tomatoes guaranteed free from race conditions and memory errors. So I'm going to talk about my experience of learning Rust to do this, and what went well and maybe not so well. So why on earth use Rust and a Raspberry Pi to irrigate your tomatoes? So I need to go back quite a bit to 1981, when I first sat in front of a computer. It was a ZX81 and I was 9 years old, and I've sat in front of lots of computers since then, starting on the obvious 1980s home computer BASIC, but my memory of that era really is doing Z80 assembly from quite an early point, through various devices, ending up doing lots of 68,000 assembly on the Amiga, where there's lots of fun hardware to play with and control. I did a CS degree and went into industry doing embedded firmware and telecoms, doing again 68,000 assembly and C code, controlling hardware for quite a few years. I did a stint doing Linux device drivers, again controlling hardware. And the last thing I did in this sort of embedded space was porting WebKit to an embedded ARM11 device. So I haven't done embedded or hardware programming seriously for quite a few years, but I do have a lot of history of C and assembly and hardware control. So I was aware of this new language, Rust, that claimed to be strong in this area, and I wanted to learn more about it. I'm not great at doing tutorials and toy projects. I need something to get my teeth into, so I looked around for something I could apply Rust to. And I was in my greenhouse one day. I grow tomatoes in the greenhouse in the summer, and it's a nice distraction from writing code, and the tomatoes you get are better than anything you can buy, so it's a worthwhile thing to do. But for purpose of this audience, I guess not enough technology. Let's apply some technology to growing tomatoes. We'll start with a Raspberry Pi. This is a Model B. We can get these solenoid water valves pretty cheaply online for about £10. These moisture sensors are resistive, so there's just a little metal track that sticks in the soil, and they come with a little board that converts that resistance into a voltage that can be measured. And for some extra data, I have a device called a BME 280, which is a combined temperature, humidity and atmospheric pressure sensor with an I2C interface. So we're going to have to write Rust code to control all this. And if that's not ambitious enough, there's no mains power anywhere near my greenhouse, so the whole thing is solar powered. Right, let's look at that device in a bit more detail. The Raspberry Pi Model B has an Broadcom 2835 system on chip. This is the same ARM11 core that was found on the original iPhone, if that's a reference. That's useful. It's clocked a good bit higher, nearly twice as fast on this device, but it's an ARM version 6 instruction set. That's 32-bit ARM. In the parlance of GCC cross compilers, it's known as ARM for the architecture, unknown for the vendor, since there's nothing proprietary here. Linux is the OS, and GNU EABI is the function calling convention of how registers in the stack are used for function parameters and the like. HF at the end means there's hardware floating point on this device. Now, in all my years of doing embedded and cross-compiling, really, so you're building on one device and compiling code to target a different device. One of the big bugbears and big problems was always getting your toolchain to work. it always involved compiling the compiler from scratch, and that involved a lot of tweaking and configuring it as well. And usually it was a pretty laborious and an unexciting job. And I'm glad to say that experience has been taken away. If you're on Ubuntu, this is enough to give you a GCC cross-compiler that can target the Raspberry Pi Model B. I happen to be on Arch Linux, and inevitably it's more complex, but it is just a series of commands. Let's ignore that. Rust up target add will add the target to Rust and Cargo, so it's aware of this target. And then in your Cargo config, a couple of lines just to say where the linker is sufficient, so that Cargo can now build with the target option to say this is what you want to build for. And if you inspect the file, which appears in a target specific debug directory, it's a 32-bit ELF ARM binary that runs directly on the Raspberry Pi. Now for actual code that I want to run on the device, I will do a release build and also strip the binary. I want to keep that size small, not least because I have a fairly flaky connection, a Wi-Fi connection to my device, which is 20 meters from my house. So I don't want to have to transfer a multi-megabyte file. Once you've got cross-compiling working, you need to write the hello world of hardware control. This code is maybe the first Rust code I wrote targeting the Raspberry Pi. It's pretty simple. We pick up the sysfs GPIO crate, and we're configuring one hardware pin in the output direction, which means we control the voltage on that pin through software. And then we toggle the voltage from 1 to 0 repeatedly with a sort of human-sized delay in between, so we can see what's happening. And then what you do is you wire that pin up to an LED, and hopefully you can see, here's the code, and here is a flashing LED with Rust code running on that Raspberry Pi. So once you get that working, it's really a matter of looking at all the other bits of hardware you've got and starting to write some drivers for them. So I started with the weather sensor device. It came with a data sheet with a big ream of C code in it for the rather elaborate way that you read the weather data from it. It seems there's a whole bunch of calibration data you have to read off the device. Then there's a process where you write some commands, wait a certain amount of time, and then read some data back, and then you do a whole bunch of maths to turn the read data and the calibration data into a temperature, a pressure, and a humidity in sensible units. But this was quite a good place to start with Rust coding, was to take some existing C that was really dealing with a lot of primitives and byte twiddling and bit twiddling, and port it to Rust and get that to work. There's a parallel track that you then go into of writing control code for the hardware and also assembling all the hardware into one board, so you can deploy this. So on this board you can see my temperature sensor down in the bottom right, the three little boards that come with the moisture sensors are sticking up at funny angles, and I said earlier the output of voltage. There is no analog inputs on the Raspberry Pi, so I have an analog digital converter chip, which you can just see behind those blue boards that are sticking up. That's an 8-channel ADC, which gives me a 10-bit number I can read for each channel. So that's the moisture reading, and then the three black and silver things sticking up on the right are Darlington transistors. These are capable of switching about an amp of current, which is sufficient to activate those solenoid valves. So that's the hardware. Here's a little bit more code for the ADC chip. I switched from sysfs GPIO to Rust IO at this point. That crate has I/O control, but it also supports the SPI bus, which is a lower level serial, another serial bus on the Raspberry Pi connector, which connects to this device. So you can see it's a very similar programming model. We send some bytes to the device, we read some bytes back, do a little bit of bit twiddling, and out comes a value, which we can actually convert right to a voltage. Now, putting the hardware together was fine, and I struggled at this point a little bit to work out how to turn my vision of the application into Rust code that represents it. So I had this vision of 4 modules that were fairly independent: the scheduler, the weather, the things that read the hardware, or you run timers and things like that. Generating events, passing to a central controller, which would then decide what to do with these events. This felt like the sort of software architecture that I've seen over the years for controlling hardware, and that's what I wanted to build. And it wasn't obvious, given all Rust's constraints on ownership and sharing of data, how to build this at first. So I kept reading through the Rust programming language book, and I came to the chapter on multi-producer single consumer channels, and that's kind of when it clicked that those things at the top should have a sender and the controller should have a receiver. I can run everything on its own thread, and that's the way that the event data ends up centralized in the controller, and it can decide to put recordings in the database. I'm using an SQLite database, and it can decide based on the current known data when to activate the valves and release some water. Now, I didn't want the data just to disappear into SQLite in a SD card 20 meters away from my house. I did want to put a web server in there with a JSON API so I could read that data out and then hopefully eventually visualize it in some way. So there is a web server in there too. If we look at the dependency list, it's fairly modest. Iron is the web server, and there's a few extra modules that go with that. I'll talk about that in a minute. Rustqlite is for SQLite, and R2D2 is the connection pool manager. So the controller and the web server can access that database. So even though this list of dependencies is relatively short, when you cargo build, there are 188 crates that build. And this did put me in mind a little bit of the NPM and to some extent the Java world, where it's very easy to pull in other people's code. And often other people's code comes with other people's code. Lots of transitive dependencies. And I've always felt this is a double-edged sword. It's nice to be able to build on what other people have done, but over time that you do have to watch that dependency list and the size of it. 188 crates feels quite large for this project. I live with it for now, but I definitely think it's something that developers need to be aware of. So Iron Framework I really liked because it has a sort of philosophy of you only pay for what you use. The Iron Framework on its own gives you virtually nothing. It lets you handle an HTTP request, as in all requests come into one handler. If you want to do routing based on paths, router is a separate module. I like this approach that you put in the parts you need and you leave out the parts you don't. So the API I exposed has current weather, history of weather between certain dates or times, and history of the moisture. We can look at the irrigation events and so on. And there's a bit of code there talking about the middleware, which is a nice feature of Iron that lets you bind your own strongly typed data into the requests, so that request handlers can do things like see the configuration of the system, which is what's happening here, and also get a database connection handle. One thing I wasn't able to do the first year, which is last year, is when I built all this, was adding a sender of events into the web server. And a sender of events into the web server would allow, say, post commands to arrive at the server and send events into the controller and, say, do things like manually irrigate the plants remotely. But my issue was, of course, the web server is multi-threaded. Each request is handled on a separate thread. Presumably they come from a pool. But sender itself doesn't implement the send trait. The normal pattern is you clone a sender and you move it into the thread where it's needed, and then it just lives there. But I needed a sender that could be moved into the I needed to be able to hold on to a copy of the sender and then copy it and move it into the handling request. I didn't work out how to do this last year, but when I revived all this code this spring, I took another look at it and I came up with a solution which is fine for this project, but I wonder whether it would be adequate in a more high performance environment. So the solution is to wrap the sender in a mutex and a reference count and store that in the middleware. And then when you want to access the sender, I lock the mutex, immediately clone the sender, and then the cloned sender gets moved into the request handling thread, and the original one remains in the middleware in the mutex. This works, but as I say, I'd be a bit wary of that mutex on a high performance system. This is what the hardware looked like last year in 2019. The Raspberry Pi there with my box of tricks in a custom box. There's a camera on there, and I added a module to iron to fork a process and capture an image from the camera, so you can see the current image over HTTP. This year it's been reformulated a little bit with a Raspberry Pi Model 0. This is a bit lower power, which helped with some of the issues I had last year, and these are also really cheap, less than £5 each, which is great because I've fried quite a few of them over my time playing with it. So we've got all this data, we've got automatic irrigation, and in my head I had this image of nice pretty graphs of temperature, of moisture levels going down, and irrigation happening and moisture levels going back up. So I wanted to be able to visualize it. Now in a real DevOps environment, you'd probably send all your data to InfluxDB and write some Grafana configuration, and you'd have lovely graphs of your data over time. But that didn't really inspire me. It wasn't what this project was about. I looked at some technologies I already knew, say Elm or React. I could write a web UI in something like that and visualize the data. And that didn't really inspire me either, because the purpose of this project was to learn Rust, really. And Rust can target WebAssembly, right? So I looked around, and of course there's loads of Rust web UI frameworks. So I tried a few out. And ended up using Seed. Really for two reasons. At the point where I was looking last spring, Seed had really good SVG support, and I wanted SVG for drawing graphs. And also I like the architecture. It's that one-way data flow like Elm or Redux, which I'll go into in a little bit in a minute. So of course, back to Rust.target add, and we're going to add wasm unknown. wasm-pack is another tool you need just to finish off that binary, and out pops a binary from Rust code that runs in the browser. So the this is the top level module in the seed UI. Just to illustrate the parts, you have a model. You have a function view, which takes a model and gives you a hierarchy of virtual DOM nodes. And those DOM nodes can generate messages. So when you click on a button, say, we generate a message, and the messages end up in the update function, which can mutate the model, causing a re-render, or generating these things called orders. And a good example of an order is an HTTP request to go and fetch more data. So I really like this way of building UIs. It seems to be catching on. If you look at Jetpack Compose or Swift UI or Flutter or any of the UI frameworks that are fashionable right now, they all work this way. So my UI is of course dark mode, being an old Linux guy, and it shows, you can see the weather data there at the top, and my plants are divided into 2 zones. Only 2 of my water valves worked in the end, so I configured it this way. There are 2 moisture sensors in the tomatoes, so you can see 2 moisture levels there, with the blue bar being an irrigation event, and 1 moisture sensor in the cucumber plants. So it's fun to look at every day and see what's going on. So what did I learn building all this? Well, maybe I'm better at software than hardware. I had a few problems with hardware in the first, certainly last year, particularly this. After about 2 weeks of use, most of the metal was gone on the moisture sensors. I realised, if I remembered my high school chemistry, I'm running a current through these metal sensors in moist soil continuously, setting up a chemical reaction. And after 2 weeks, the corrosion had completely ruined these probes. So I took the thing apart and added another transistor so I can switch the power to those probes on and off. So I switched the power on for about 20 milliseconds, read the current voltage through the ADC, and then power them back down. And that solved that problem. I did spend a lot of time fiddling with this thing, mostly with the hardware, but also with the code. And you're meant to look after your tomato plants as you're growing tomatoes. They looked a bit messy last year. You can see there's fruit, but I hope to do better than that this year. And of course, I think the main lesson is that Rust was an excellent choice for this project. None of the problems I have involved software stability. The software just works. The learning curve of building something relatively complex in Rust is very real. It takes some time to get your head around how to structure an application in the right way, but the payoff is worth it in stability and in performance. And also Rust was just at home doing the hardware control and the web serving of a JSON API, and also the web UI itself. Rust tackled those problems just great in each case. So I don't know if it's useful for anyone without the hardware, but the code is all available on GitHub here. If you have any comments, contact me there or through Twitter. And if you want to see some more details on this, I did write some posts on dev.to last spring as I was building all this, so you can read through those and get some more detail. And that's my project on Pirrigator.